All right, welcome. In this problem, we're going to take a look at a reaction mechanism where the second step is the slow step. And we got some questions here. So we got a mechanism. Notice the first step is fast, the second step is slow. The first question asks us to write the balanced equation for the overall reaction. So when a question asks us for the overall reaction, what we're doing is we're just considering those two steps and we're adding them up just like we would add together an equation like in algebra. So you basically take everything on the left. So there's an A, there's two C's, then there's A, C2, and then there's A. So everything on the left, and then I'm going to combine everything on the right, and then I'm going to simplify things. So I'm going to look for things that maybe cancel out or add up. So notice how I've got an AC2 on the left and on the right. And then over on the right, notice how I have two A's. So instead of writing A plus A, I'm going to rewrite it as 2A and 2C combined to make 2AC. So this is what we call the overall reaction. And then intermediates. So intermediates are things that are made in an earlier step and used up in a later step, and they don't show up in the overall reaction. So in this example, it looks like AC2 is an intermediate. And again, if I had to like write down, how I know something is an intermediate, what we're saying is it's, made in an early step and then used up. Other thing to look for is that it does not show up in the overall reaction. So it's not a reactant or a product really, because the amount of it overall doesn't change. Like it's made, then used up right away. Okay, next one, write the rate law. So the rate law is determined by who's in the slow step of the reaction mechanism. So first let's look at who's in the slow step. So if we look at the slow step, we're going to see, okay, the rate law is going to be rate equals some constant K times the concentration of things in the slow step. So there's 1A and 1AC2 in the slow step. They're both going to be first order. So that's just my starting point with my rate law, is I'm going to say, okay, I got 1AC2 and 1A in the slow step of my mechanism. But I should notice I just said that AC2 is an intermediate, and I can't have an intermediate as part of my rate law. So whenever I have an intermediate in my rate law, which usually happens if the second step is the slow step, I'm usually going to have an intermediate in there. Then what I do is I define the intermediate in terms of the reactants in the previous step. So what that means is if you look back here in this first step here, is I'm going to write a little equality here, is I'm going to say in the first step, in order to make AC2, I combine 1A and 2 C's. So you can think of this as like the equation for this first step. So 1A and 2 C's makes 1AC2. So when I go back here into this rate law, wherever I see AC2, I'm going to substitute in 1A and 2 C's. So my overall rate law is K, and then wherever I see AC2, I'm going to substitute 1A and 2 C's, and then I already have an A. So look at that, we're actually going to simplify it. So we're going to say rate equals K A squared C squared. So this is my overall rate law for the reaction. So again, when the second step is slow, usually there's going to be intermediate involved. So you go back in and say, okay, what made the intermediate? And then you substitute in these things for whenever you see the intermediate. And you might notice in this case that the rate law, these exponents happen to match the overall reaction, but that's not always going to be true. So again, the way we figure out what the exponents are is we have to look at the mechanism, or we have to be given some experimental data. Sometimes they end up matching the overall coefficients, and sometimes they don't. I also should point out that we can simplify this reaction even more, actually, as I'm looking back at this. We could write this as A plus C makes AC is actually a better way to write this. Okay. So the for D, what would happen to the rate if all reactants were doubled? So notice how my rate law is this. Rate is equal to K A squared times C squared. And so if I were to double A and double C, it would go up by 4 times 4. It would be 16 times faster. Okay. Thanks for watching.